Hello friends, in this session we discuss sum that contain infinitely many terms. The most familiar examples of such sum occur in the decimal representation of real numbers. For example, when we write 1 upon 3 in the decimal form, 1 upon 3 equal to 0.3333 etc. We mean 1 upon 3 equal to 0.3 plus 0.03 plus 0.003 plus 0.0003 plus etc., which suggests that the decimal representation of 1 upon 3 can be viewed as a sum of infinitely many real numbers, which we will shortly start to call as a series. A series is, informally speaking, the sum of the terms of a sequence. In this session, we define series, their convergence and consider various convergence tests. To introduce the series, we need the concept of sequence already discussed in the previous sessions. We know that 1 plus 1 equal to 2. To add 3 ones, we proceed as follows: 1 plus 1 plus 1 equal to 1 plus 1 plus 1, which is equal to 2 plus 1, which is equal to 3. We add 4 ones by 1 plus 1 plus 1 plus 1 equal to 1 plus 1 plus 1 plus 1, which is equal to 3 plus 1, which is equal to 4. Continuing like this, if we are asked to add n numbers of ones, then 1 plus 1 plus etc. plus 1, n summons equal to n. But if we are asked to add the terms of the sequence 1, 1, 1, 1 etc., then it may appear in the form 1 plus 1 plus 1 plus 1 plus etc. Is this expression gives a real number? That is there any real number L such that 1 plus 1 plus 1 plus 1 plus etc. equal to L? We will continue this discussion shortly. Zeno of Elea was a great philosopher and mathematician of the 5th century BCE. One of the paradoxes suggested by Zeno is as follows: a runner wants to run a certain distance, for example 1 kilometer. In order to reach his destination, he has to cross the midpoint at a distance half kilometer. That is, first he has to cover a distance of half kilometer. To cover the remaining half kilometer, he has to first cover its half distance, which is 1 upon 4 kilometer. The remaining 1 upon 4 kilometer can be covered only by covering its half distance, which is 1 upon 8 kilometers, and so on. That is, in total he has to cover the distance 1 upon 2 plus 1 upon 4 plus 1 upon 8 plus 1 upon 16 plus etc. During the time of Zeno, infinite sum of the above form to produce a finite real number was considered paradoxical. Hence, Zeno argued that the runner cannot reach the final goal. This paradox concludes that any motion is impossible, which is wrong. This paradox was resolved using the concept of limit during the 19th century, and we will describe it shortly. The above discussion gives us two cases of infinite additions, namely 1 plus 1 plus 1 plus 1 plus etc. and 1 upon 2 plus 1 upon 4 plus 1 upon 8 plus 1 upon 16 plus etc. Such formal sums are examples of infinite series, which we define as follows: if u1, u2, u3 etc., un etc. be a sequence of real numbers, then u1 plus u2 plus u3 plus etc. plus un plus etc. is called an infinite series, or briefly a series. Un is the nth term of the series. An infinite series u1 plus u2 plus u3 plus etc. plus un plus etc. is denoted by summation un n from 1 to infinity. The sum Sn equal to u1 plus u2 plus etc. plus un, that is the sum of the first n terms of the series, is called the nth partial sum of the series, summation un n from 1 to infinity. If Sn is the nth partial sum of the series, summation un n from 1 to infinity, then the sequence S1, S2, S3 etc. Sn etc. is called the sequence of partial sum of the series. We find first, second, third and nth partial sum of the series, summation un n from 1 to infinity, where un equal to 1 upon 2 power n minus 1. Since un equal to 1 upon 2 power n minus 1, the given series is summation un n from 1 to infinity equal to 1 plus 1 upon 2 plus 1 upon 2 square plus 1 upon 2 cube plus etc. plus 1 upon 2 power n minus 1 plus etc. The first partial sum is given by S1 equal to U1, which is equal to 1. The second partial sum is given by S2 equal to U1 plus U2, which is equal to 1 plus 1 upon 2, which is equal to 3 upon 2. The third partial sum is S3 equal to U1 plus U2 plus U3, which is equal to 1 plus 1 upon 2 plus 1 upon 2 square, which is equal to 1 plus 1 upon 2 plus 1 upon 4, which is equal to 7 upon 4. The nth partial sum is given by Sn equal to U1 plus U2 plus etc. plus Un, which is equal to 1 plus 1 upon 2 plus 1 upon 2 square plus etc. plus 1 upon 2 power n minus 1, which is equal to 1 minus 1 upon 2 whole power n upon 1 minus 1 upon 2, which is equal to 2 minus 1 upon 2 power n minus 1. We find the nth partial sum of the series summation un n equal to 1 to infinity, where un equal to negative 1 power n. The given series is summation un n from 1 to infinity equal to negative 1 plus 1, negative 1 plus 1, negative 1 plus etc. plus negative 1 power n plus etc. The nth partial sum is given by Sn equal to negative 1 if n is odd, 0 if n is even. Convergence and divergence of series. The convergence or divergence of a series is determined by examining the behavior of the sequence of partial sums of the series. Let sequence Sn be a sequence of partial sum of the series summation un n from 1 to infinity, which is equal to u1 plus u2 plus u3 plus etc. plus un plus etc. If the sequence Sn converges to a limit S, then the series is said to converges to S, and S is called the sum of the series. In this case, the series is said to be summable. We denote this by writing S equal to summation un n from 1 to infinity. If the sequence of partial sums diverges, then the series is said to be diverge. A divergent series has no sum, and we say that the series is not summable. We test the convergence of the series 5 minus 4 minus 1 plus 5 minus 4 minus 1 plus 5 minus 4 minus 1 plus etc. Let Sn be the sum of the first n terms of the series. Then Sn equal to 0 if n equal to 3m, 5 if n equal to 3m plus 1, 1 if n equal to 3m plus 2. Here the sequence of partial sum is 5, 1, 0, 5, 1, 0 etc., which does not converge. Hence, the series is divergent. As the sequence of partial sum has an oscillatory nature, we say that the series is oscillatory. As promised at the beginning, let us try to answer the question. Is there any real number L such that 1 plus 1 plus 1 plus etc. equal to L? Here the nth term of the series is un equal to 1. Then the nth partial sum is Sn equal to 1 plus etc. plus 1 n sum ns, which is equal to n. This the sequence Sn of partial sum is the sequence n which diverges, because it outgrows every real number m. We denote it by writing limit of Sn as n approaches infinity is positive infinity. Hence, the series also diverges. As limit of Sn as n approaches infinity is positive infinity, we say that the series diverges to positive infinity. This shows that there is no real number L such that 1 plus 1 plus 1 plus etc. equal to L. We show that the series 1 square plus 2 square plus 3 square plus etc. plus n square plus etc. diverges to positive infinity. Let un equal to n square. Then the nth partial sum is Sn equal to 1 square plus 2 square plus etc. plus n square, which is equal to n into n plus 1 into 2n plus 1 upon 6. As the terms of the sequence Sn of partial sums outgrows every real number m, it diverges, and hence the series diverges to positive infinity. We show that the series summation n plus 1 upon n, where n is from 1 to infinity, which is equal to 2 upon 1 plus 3 upon 2 plus 4 upon 3 plus etc. plus n plus 1 upon n plus etc. diverges. The given series diverges because the sequence of partial sum of the given series diverges. An arithmetic series is the sum of an arithmetic sequence, a sequence with a common difference between each two consecutive terms. Then its sequence of partial sums diverges because it outgrows every real number L. Hence, the arithmetic series also diverges. The series summation a r power n, where n is from 0 to infinity, equal to a plus ar square plus etc. plus a r power n minus 1 plus etc. called geometric series, and is converges if absolute value of r less than 1. The nth partial sum of the series is given by Sn equal to a plus ar square plus etc. plus a r power n minus 1, which is equal to a into 1 minus r power n upon 1 minus r, which is equal to a upon 1 minus r minus a r power n upon 1 minus r, equation number 1. We note that when absolute value of r less than 1, r power n approaches to 0. Hence, limit of a r power n upon 1 minus r as n approaches infinity equal to a upon 1 minus r into limit of r power n as n approaches infinity, which is equal to a upon 1 minus r into 0, which is equal to 0 for absolute value of r less than 1. Hence, from 1 we obtain limit of Sn as n approaches infinity equal to a upon 1 minus r. That is, the sequence Sn of partial sums converges to a upon 1 minus r. Hence, the given series also converges to a upon 1 minus r for absolute value of r less than 1. In other words, summation a r power n minus 1, where n is from 1 to infinity equal to a upon 1 minus r for absolute value of r less than 1. In view of these results, we can deal 1 plus 1 upon 2 plus 1 upon 2 square plus 1 upon 2 cube plus etc. plus 1 upon 2 power n minus 1 plus etc. easily. Taking a equal to 1, r equal to 1 upon 2 in the geometric series and get the sum 2. We show that the series 1 upon 9 plus 1 upon 27 plus 1 upon 81 plus etc. converges. Find its sum. The given is a geometric series with a equal to 1 upon 9 and r equal to 1 upon 3. Here absolute value of r strictly less than 1. Hence, the series is convergent and its sum is given by 1 upon 9 plus 1 upon 27 plus 1 upon 81 plus etc. equal to 1 upon 9 upon 1 minus 1 upon 3, which is equal to 1 upon 6. With our definition of convergence of series, let us reconsider the expression 1 upon 3 equal to 0.3 plus 0.03 plus 0.003 plus 0.0003 plus etc. And we are going to show that this equation is true by showing that the series on the right hand side converges to 1 upon 3. The series on the right hand side is a geometric series with a equal to 0.3 and r equal to 0.1. Here absolute value of r less than 1, hence the series is convergent and its sum is given by 0.3 upon 1 minus 0.1, which is equal to 0.3 upon 0.9, which is equal to 1 upon 3 as we expected. Now, let us try to answer Zeno's paradox. Consider the series 1 upon 2 plus 1 upon 4 plus 1 upon 8 plus 1 upon 16 plus etc. That is, the series 1 upon 2 plus 1 upon 2 square plus 1 upon 2 cube plus 1 upon 2 power 4 plus etc. The given is a geometric series with a equal to 1 upon 2 and r equal to 1 upon 2. Here absolute value of r less than 1, hence the series is convergent and its sum is given by 1 upon 2 upon 1 minus 1 upon 2, which is equal to 1. This says that the distance to be covered by the runner, which is the sum of the infinite series 1 upon 2 plus 1 upon 2 square plus 1 upon 2 cube plus 1 upon 2 power 4 plus etc. is 1 kilometer, which we always expect. We show that the series summation negative 1 power n into 5 upon 4 power n as n from 1 to infinity equal to negative 5 upon 4 plus 5 upon 16 minus 5 upon 64 plus etc. has the sum negative 1. The given is a geometric series with a equal to negative 5 upon 4 and r equal to negative 1 upon 4. It converges to a upon 1 minus r, which is equal to negative 5 upon 4 upon 1 plus 1 upon 4, which is equal to negative 1. Suppose you drop a ball from a meter above a flat surface. Each time the ball hits the surface after falling a distance h, and it rebounds a distance rh where r is positive but less than 1. Find the total distance the ball travels up and down. Discuss the particular case with a equal to 6 meter and r equal to 2 upon 3. Before the first impact, the ball falls a distance a meters. After the first impact, the ball rebounds a distance ar and again come back to the floor falling a distance ar. Thus, before the second impact, total distance covered by the ball is a plus ar plus ar. After the second impact, the ball rebounds a distance ar into r, which is equal to ar square, and again come back to the floor falling a distance ar square. Thus, before the third impact, total distance covered by the ball is a plus ar plus ar plus ar square and continue the process. Hence, the total distance is s equal to a plus ar plus ar square plus ar cube plus etc., which is equal to a plus 2ar plus 2ar square plus 2ar cube plus etc., which is equal to a plus 2ar upon 1 minus r, since sum of the geometric series 2ar plus 2ar square plus 2ar cube plus etc. is 2ar upon 1 minus r, which is equal to a times 1 plus r upon 1 minus r. If a equal to 6 and r equal to 2 upon 3, the distance is s equal to 6 times 1 plus 2 upon 3 upon 1 minus 2 upon 3, which is equal to 6 times 5 upon 3 upon 1 upon 3, which is equal to 30 meters. Telescoping series. The advantage of geometric series is that if it is convergent, then its limit can be easily evaluated. Unfortunately, formulas like the one for the sum of convergent geometric series are rare, and we usually have to settle for an estimate of a series sum. The next example, however, is another case in which we can find the sum exactly. We discuss the convergence of the series 1 upon 1 into 2 plus 1 upon 2 into 3 plus 1 upon 3 into 4 plus etc. plus 1 upon n into n plus 1 plus etc. Also, we find its sum. Here un equal to 1 upon n into n plus 1. By partial fraction, 1 upon n into n plus 1 equal to a upon n plus b upon n plus 1, which gives 1 equal to a into n plus 1 plus bn. Putting n equal to negative 1, we have b equal to negative 1, and putting n equal to 0, a equal to 1. Hence, un equal to 1 upon n minus 1 upon n plus 1. The nth partial sum of the series is given by Sn equal to u1 plus u2 plus etc. plus un, which is equal to 1 upon 1 minus 1 upon 2 plus 1 upon 2 minus 1 upon 3 plus 1 upon 3 minus 1 upon 4 plus etc. plus 1 upon n minus 1 upon n plus 1, which is equal to 1 upon 1 minus 1 upon 2 plus 1 upon 2 minus 1 upon 3 plus 1 upon 3 minus 1 upon 4 plus etc. plus 1 upon n minus 1 upon n plus 1, which is equal to 1 minus 1 upon n plus 1. Hence, limit of Sn as n approaches infinity is limit of 1 minus 1 upon n plus 1 as n approaches infinity, which is equal to 1 minus 0 equal to 1. Since the sequence of partial sum converges to 1, the series also converges to 1. Hence, we can write 1 upon 1 into 2 plus 1 upon 2 into 3 plus 1 upon 3 into 4 plus etc. plus 1 upon n into n plus 1 plus etc. equal to 1. The harmonic series. Theorem 1. The series summation 1 upon n from 1 to infinity equal to 1 plus 1 upon 2 plus 1 upon 3 plus etc. plus 1 upon n plus etc. called the harmonic series diverges. Now we give a proof. A simple proof will be given in a later session. The given is a series of non-negative terms. Hence, to show that the series is divergent, it is enough to show that there is no upper bound for the partial sum of the harmonic series. For this, we group the terms of the series in a following way. 1 plus 1 upon 2 plus 1 upon 3 plus 1 upon 4 plus 1 upon 5 plus 1 upon 6 plus 1 upon 7 plus 1 upon 8 plus 1 upon 9 plus 1 upon 10 plus etc. plus 1 upon 16 plus etc. We note that S2 equal to 1 plus 1 upon 2 greater than 1 upon 2 plus 1 upon 2, which is equal to 2 upon 2. S4 equal to S2 plus 1 upon 3 plus 1 upon 4 greater than S2 plus 1 upon 4 plus 1 upon 4, which is equal to S2 plus 1 upon 2 greater than 2 upon 2 plus 1 upon 2 equal to 3 upon 2. S8 equal to S4 plus 1 upon 5 plus 1 upon 6 plus 1 upon 7 plus 1 upon 8, which is greater than S4 plus 1 upon 8 plus 1 upon 8 plus 1 upon 8 plus 1 upon 8, which is equal to S4 plus 1 upon 2 strictly greater than 4 upon 2. Therefore, S of 2 power 4 equal to S16, which is equal to S8 plus 1 upon 9 plus 1 upon 10 plus etc. plus 1 upon 16, which is strictly greater than S8 plus 1 upon 16 plus 1 upon 16 plus etc. plus 1 upon 16 2 power 3 summons, which is equal to S8 plus 8 upon 16, which is equal to S8 plus 1 upon 2 strictly greater than 5 upon 2. Therefore, S of 2 power n greater than n plus 1 upon 2. If m is any constant, we can find a positive integer n such that n plus 1 upon 2 strictly greater than m. But for this n, S 2 power n greater than n plus 1 upon 2, which is greater than m. So, that no constant m is greater than or equal to every partial sum of the harmonic series. Hence, the harmonic series diverges. Algebraic properties of infinite series. When we have two convergent series, we can add them term by term, subtract them term by term, or multiply them by a constant to make new convergent series. We state this in a following result. We omit the proof here, but we mention that the rules gives below follow from the analogues rules for sequences. Theorem. If summation a n equal to a and summation b n equal to b are convergent series, then first one sum rule, summation a n plus b n equal to summation a n plus summation b n, which is equal to a plus b. Second one difference rule, summation a n minus b n equal to summation a n minus summation b n, which is equal to a minus b. Third one constant multiple rule, summation k times a n equal to k times summation a n, which is equal to k times a. We remark that from constant multiple rule, if C is a non-zero constant, then the series summation u n and summation c times u n both converges or both diverge. We use the above rules to find the sum of the series summation 3 n minus 1 upon 6 power n minus 1 n from 1 to infinity, which is equal to summation 3 power n minus 1 upon 6 power n minus 1 where n from 1 to infinity, which is equal to summation 1 upon 2 power n minus 1 minus 1 upon 6 power n minus 1 where n from 1 to infinity, which is equal to summation 1 upon 2 power n minus 1 where n from 1 to infinity minus summation 1 upon 6 power n minus 1 where n from 1 to infinity using difference rule, which is equal to 1 upon 1 minus 1 upon 2 minus 1 upon 1 minus 1 upon 6, as each are geometric series with a equal to 1, r equal to 1 upon 2 and a equal to 1, r equal to 1 upon 6 respectively, which is equal to 2 minus 6 upon 5, which is equal to 4 upon 5. Adding or deleting terms. We can always add a finite number of terms to a series or delete a finite number of terms without altering the series convergence or divergence. Although in the case of convergence, this will usually change the sum. This is described in the following result. Theorem. Convergence or divergence is unaffected by deleting a finite number of terms from a series. In particular, for any positive integer k, the series summation u n n from 1 to infinity equal to u1 plus u2 plus etc. summation u k equal to uk plus 1 plus uk plus 2 plus etc. where n from k to infinity both converges or both diverges. Since the geometric series summation 1 upon 5 power n from 1 to infinity equal to 1 upon 5 plus 1 upon 25 plus 1 upon 125 plus summation 1 upon 5 power n from 4 to infinity etc. equation 1 converges. The series summation 1 upon 5 power n from 4 to infinity equal to summation 1 upon 5 power n from 4 to infinity minus 1 upon 5 minus 1 upon 25 minus 1 upon 125 obtained by deleting first 3 terms of the series 1 converges. Determine whether the series summation 1 upon n from 100 to infinity converge or diverge. Summation 1 upon n from 100 to infinity diverges since it is the series obtained by deleting the first 99 terms from the divergent harmonic series summation 1 upon n from 1 to infinity. Reindexing. As long as we preserve the order of its terms, we can reindex any series without altering its convergence. To raise the starting value of the index h units, replace the n in the formula for an by n minus h. Summation n from 1 to infinity equal to summation n minus h, n equal to 1 plus h to infinity, which is equal to a1 plus a2 plus a3 plus etc. To lower the standing value for the index h units, replace the n in the formula for an by n plus h. Summation n from 1 to infinity equal to summation n plus h, n equal to 1 minus h to infinity, which is equal to a1 plus a2 plus a3 plus etc. For instance, with index h equal to 0, summation n from 0 to infinity equal to a0 plus a1 plus a2 plus a3 plus etc. Let's summarize the session. In this session, an introduction to series of real numbers is made. Convergence or divergence of series is defined and illustrated through various examples. Algebraic properties of infinite series such as sum, difference, product and quotients of two series have been discussed. We have observed that convergence or divergence is unaffected by deleting a finite number of terms from a series. It's observed that as long as we preserve the order of its terms, we can reindex any series without altering its convergence. Hope you enjoy the session. See you next time. Until then,